So, what powers pretty much everything in your life? From your morning coffee order to the entire global financial market. It's not magic, it's software. But let's be real, if it's so important, why does it so often feel kind of broken? Well, today, we're going to pull back the curtain on software engineering to figure out the secrets that separate the digital marvels from the digital disasters. I mean, it is almost impossible to overstate this. Seriously. Think about the big stuff, like the national infrastructure that brings you power and water, the global financial system. And then think about your life, the shows you stream, the phone in your pocket. It is all run by software. It's like this invisible engine humming along underneath our entire society. And yet, for something so critical, all we ever hear about are the failures, right? Security breaches, annoying bugs, projects that are years late and billions over budget. The reason? Well, the main reason comes down to one thing: complexity. The more we ask of our software, make it faster, bigger, more connected, the challenge of actually building it reliably just goes through the roof. Okay, so this is where software engineering really enters the picture. And look, this isn't just some fancy buzzword for coding. It's the actual discipline that was created to tame all of that complexity and to move us from just chaotically making stuff to predictably and reliably constructing it. You got to pay attention to the words here: systematic, disciplined, quantifiable. See, that isn't the language of art. It's the language of engineering. It's really the difference between a hobbyist building a little garden shed and a whole team of professionals building a skyscraper. Yeah, both are creating something, but only engineering gives you that repeatable process to make sure the thing you build doesn't just work today, but that it's going to last. So how do you manage all that complexity? Well, the very first step is having a process, a kind of roadmap that guides your team from a vague idea all the way to a finished product. And in the software world, there are two main schools of thought for what that map should look like. On one side, you've got the old school, traditional waterfall model. It's totally linear. You do all the planning, get it perfect, then you do all the design, get that perfect, then you start coding. One phase has to be completely finished before the next one starts. And then there's Agile, which is an approach built for a much less predictable world. It's all about working in small, fast, flexible cycles. And this right here is the absolute key to understanding Agile. In our world, business needs user feedback, new technology. It can all change in a flash. A rigid, year-long plan can be totally obsolete before you've even written the first line of code. Agile is built to embrace that change, to deliver working pieces of software super frequently so the team can learn and adapt on the fly. Now, to make this a little more real, let's look at Scrum, which is a super popular Agile framework. So instead of a massive year-long plan, all the work is broken down into a prioritized list called a backlog. A small team grabs tasks from the top of that list and works in these short cycles called sprints, usually just a couple of weeks long. And at the end of every single sprint, they have a real working piece of the product to show for it. It creates this amazing rhythm of constant delivery and feedback. It's a structured way to deal with all the uncertainty of a project. But, a great process isn't much good without a clear plan. Before anyone writes a single byte of code, you need a plan. And in software, this is the world of system modeling and architecture. This journey from a vague idea to a solid blueprint, well, it's a process. It starts with elicitation, which is really just a fancy word for talking to everybody involved to really understand the problem you're trying to solve. Then comes specification, where you turn all those conversations into formal, crystal clear documents. And finally, modeling brings it all to life with diagrams that let you see the system's structure and how it'll behave before you've even built a single piece of it. And inside that process, there's this super important distinction you have to make. Functional requirements describe what the system does. The features, like users can search for patient records. But non-functional requirements describe how well it needs to do those things. We're talking performance, security, reliability. Because let's face it, a system that technically works but is crazy slow or totally insecure is still a failure, right? So once you know what to build, you have to decide on its high-level structure, its architecture. The good news is you almost never have to invent this from scratch. Engineers use what are called architectural patterns. These are proven, reusable blueprints for common problems. Think of it like having standard designs for a skyscraper or a suspension bridge or just a regular house. You pick the right pattern for the job. A classic example, one you are literally using right now, is the client-server pattern. A client, like your web browser, asks for stuff from a central server. The huge advantage is that you can have servers all over the world. The disadvantage? Well, that server is a single point of failure. If it goes down, everything stops working. Good engineering is all about knowing these trade-offs and picking the right pattern for your specific problem.
Okay, so you've got a process and you've got a blueprint, but how do you make sure that the final thing you build is actually safe, secure, and reliable? This gets us to maybe the most critical part of engineering, building systems that you can actually trust.
To really understand the stakes here, let's talk about a classic safety-critical system, an insulin pump. Now, this isn't a game or a social media app. In this case, a software failure can cause direct physical harm, which is a pretty stark reminder of why this whole discipline is so incredibly important.
The way it works is actually pretty simple. A software controller sends out a pulse and the pump delivers 1 unit of insulin. But to deliver the correct dose over time, that software has to be unbelievably precise and reliable. A bug here isn't just an inconvenience, it's a legitimate medical emergency.
And this leads us to a really fundamental and kind of humbling concept in engineering. This quote from the sociologist Charles Perrow is just profound. What he's saying is that you can't just hope for the best. You have to design your system with the assumption that failures will happen. The goal isn't to build a perfect system that never fails, but to build a resilient one that can handle failures gracefully when they inevitably occur.
So, how do engineers respond to that reality? With proactive defense. These are key design principles for security. Defense in depth means you have multiple layers of protection, not just one front door lock. Fail securely means that if a part of the system breaks, it shuts down in a safe way, not in a way that causes more damage. It's all about designing for failure right from the very beginning.
And of course, you have to actually find the flaws. And here's something people mix up all the time. Testing and debugging are not the same thing. Testing is the scientific process of finding out if a problem exists. Debugging is the detective work of finding the exact cause of a problem you already know about and then fixing it. They are two totally separate but equally critical skills. So, as you can probably see by now, the actual act of writing code is really just the tip of the iceberg. Building great software is all about navigating these massive, complex challenges that are lurking just beneath the surface. Which brings us to the most important takeaway of all. Software engineering is what we call a socio-technical discipline. Socio and technical. Yes, it's about managing technical complexity, for sure, but it's also about managing people, communication, changing business goals, and even office politics. True success depends on balancing all of those things all at the same time. And that leaves us with one last big question to think about. We have become incredibly good at building software that is smart. But as software gets woven more and more deeply into the very fabric of our society, the real challenge is this: how do we build software that is also wise? And that, right there, is the question that's going to define the next generation of software engineering.